Hello students, good time to all. I am Chandan Kumar Pradhan. Welcome to the YouTube channel Chandan Physics. In this video, we are going to discuss functions of a complex variable. Let's begin. Generally, we know a complex number z is represented as x plus iy, that is in Cartesian form, and z is equal to r cos theta plus I sin theta, that is in the polar form. Further, z is equal to r into e to the power I theta, which is the exponential form. As we draw the coordinate axis, that is x axis, which is real axis, y axis, that is imaginary axis, and a point P. If it has the coordinate xy, so it represent that portion as y, that portion as x. But when that point P represent the coordinate as r and theta in terms of polar, so that portion represent r, that angle represent theta, which is the argument of that complex number. Now, f of z is a complex, is a function. What type of function? Of a complex variable z. Complex variable z, and it is denoted by w, that is w is equal to function of z, f of z. Here we say x plus iy, which is the complex variables. These are the complex variables. Complex variables. So f of z is written as u is a function of xy plus I v as a function of xy. That portion u xy is the real part, and I v of xy, that for imaginary part, where u xy and v xy, u and v are the functions of real in x and y. U and v are real functions x and y. Similarly, when we prefer z is equal to r into e to the power I theta, that in the polar form, in that of case, again, when z is equal to r into e to the power I theta, then the function w is a function of z, that is f of r into e to the power I theta, and that can be also written as u as a function of r theta, I into v as a function of r theta. that is the representation of a complex variable. So f of z is a function of complex variable z, then it is denoted by w. So w is a function of f of z which is represented as u of xy plus I v into xy, v of xy, as u and v are the real functions in terms of x and y, that be the real part, that one be the imaginary part. Taking some examples related to this. First example, write f of z is equal to z square, that is the given function, in the form of u r theta and v r theta. The solution you have to write here. Given the function f of z is equal to z square, but in polar form. Z is equal to r into e to the power I theta. Therefore, f of z, f of r into e to the power I theta is equal to, that function is the square of that given function z square. So it will be r e to the power I theta square, that is r square e to the power 2 I theta. At e to the power 2 I theta is written as r square cos 2 theta plus I sin 2 theta, which implies that function f of r e to the power I theta is equal to r square cos 2 theta plus I r square sin 2 theta. So that portion represent as u as a function of r theta, this portion represent as v as a function of r theta. In this way, that particular given function we can write in terms of u r theta and v r theta. Next question, express the function in the form of u xy plus I v of xy, means separating the real and imaginary parts. That function f of z is equal to z square. Therefore, we taken as f of z is equal to as x plus iy square, which is equal to x square plus I square y square plus 2yxy, which is equal to x square minus y square plus I of 2xy. That part gives rise to u of xy. So u of xy, and that part gives v of xy. Next, we have to solve f of z is equal to modulus of z square. Here f of z, that for question number 1, that for question number 2, f of z is equal to magnitude of z square, but magnitude of z is equal to x square plus y square under root. Therefore, f of z is equal to x square plus y square, square of the magnitude. We have x square plus y square. Now it is written in terms of u plus xy, u plus xy plus I v of xy. comparing that side, we have therefore u of xy will be x square plus y square, that is the real part. So, imaginary part v of xy, there will be no such imaginary part, that part will be 0. In this way we show the functions of a complex variable separating their corresponding terms. Generally, as we studied in case of general functions as limit, continuity and differentiability, here in case of complex variables all such mathematical operations hold good. We have to discuss one by one. First one is limit. What is limit in case of complex variables? If f of z, z as you know that is a complex number, and that is a complex variable f of z, be a single valued function and defined at all points in some neighborhood of the point z0, z0 neighborhood point, then the limit of f of z where z approaches to z0, let that limit value is w0 or w0, that limit can be represented as limit z tends to 0 or z approaches to 0 of f of z, that leads to w0. By taking some examples, we can easily understand the concept of limit in case of complex variables. We have two functions to evaluate the limit. First question, as limit z approaches to 1 or z tends to 1 of z square minus 1 divided by z minus 1. Generally, we can easily evaluate the limits. First question, as limit z tends to 1 z square minus 1 divided by z minus 1. Now, limit z tends to 1, in that of numerator part z square minus 1 is the product of z plus 1 and z minus 1 divided by z minus 1, z minus 1, z minus 1 cancel out. So, it has limit z tends to 1 z plus 1 divided by 1. Now, we can evaluate the limit as 1 plus 1 which is equal to 2. So, limit of that complex variable, complex function can be easily evaluated. Next question, question number 2, question number II, limit z tends to minus 1 z plus 1 divided by I z plus 3. Here we can easily evaluate that limit by putting z as minus 1. So, we have minus 1 plus 1 divided by I minus 1 plus 3. So, 0 divided by minus I plus 3, 0 divided by something, the result will be 0. Let us take another question, evaluating the limit z tends to minus I z fourth minus 1 divided by z plus I. Third question, evaluating the limit z tends to minus 1 z to the power fourth minus 1 divided by z plus I. So, limit z tends to minus 1, upper part means the numerator 1 is z square minus 1 divided by z plus I, which is equal to limit z tends to minus 1, that is a square minus b square a plus b whole into a minus b formula is used. So z square plus 1 whole into z square minus 1. A square minus b square a plus b whole into a minus b divided by z plus I. Now we can evaluate the limit by putting z as minus 1. So minus 1 square plus 1 minus 1 square minus 1 divided by z square plus 1 z square minus 1 divided by z plus that not I, let that one be 1. The question is z plus 1 is here, z plus 1 z plus 1 z plus 1. So again limit z tends to minus 1, here z square plus 1, that is the product of z plus 1 whole into z minus 1 divided by z plus 1 z plus 1 z plus 1 cancel out. So the limit can be easily evaluated by putting z as minus 1 square plus 1 whole into minus 1 that is 2 into minus 2, result as minus 4. Here z as minus I, okay, that is minus I minus I minus I minus I minus I square, here minus I a square minus 1 plus 1, that is 2, here minus I minus 1 minus I minus 1. Just we have to know how to evaluate the limit. Here that question is wrong one, therefore the result whatever we expect. Okay, next one, continuity. The function f of z of a complex variable z is said to be continuous at the point z0 if for any given positive number epsilon we can find a number delta such that f of z minus f of z0 magnitude less than equal to epsilon for all points of z of that given domain which is satisfying that term, the magnitude of z minus z0 is less than delta. Therefore, we say f of z is said to be continuous at that given point, the point as we say z naught, if that limiting value is equal to f of z naught. Limit of z tends to z naught of f of z is equal to f of z0. If the limiting value will be same, then we say at that particular point that given function is continuous. We can easily understand it by taking an example related to this. So the question is, so that the function f of z is equal to z square is continuous for all values of z. To solve that question, you have to prefer z is equal to x plus iy. Therefore, f of z is equal to x plus iy square is equal to x square plus I square y square plus 2yxy, which implies f of z is equal to, separating the terms as x square, I square is equal to minus 1 minus y square plus I 2xy, at the real part, that one with the imaginary part. So, f of z is written as u plus uxy plus iv xy is equal to x square minus y square plus I 2xy. Comparing both sides, we get u xy is equal to x square minus y square, v of xy is equal to 2xy. Here the real valued function u and v are the real valued functions. U and v of two real values x and y are continuous for all values of x and y. Therefore, the given function as f of z is equal to z square is continuous for all values of z. Okay. Now, we have to show for all values of z that given function f of z is equal to z square is continuous. Next, differentiability in case of complex variables. Let f of z is a single valued function of variable z, then its differentiation means f dash z is equal to limit delta z tends to 0, or we can say delta z approaches to 0, whereas f of z plus delta z some increment in z minus f of z divided by delta z, as generally we relate to the derivative of general functions, that same in case of complex variables, provided that the limit exists. The limit, as we evaluate limit del z tends to 0 of that particular function must be exist, and it is independent of the path along which delta z tends to 0. Let us take an example related to differentiability in case of complex variables. The question is given to us, so that if f of z is equal to z to the power n, then its differentiation f dash z first order derivative is equal to n z to the power n minus 1, whereas n is a positive integer. Now, the solution. Given that f of z is equal to z to the power n. So, some increment in z, that function z plus del z is equal to z plus delta z to the power n. Now f of z plus delta z minus f of z, we have to evaluate that limiting value. So, limiting value f of z plus delta z minus f of z, f of z plus delta z minus f of z, f of z plus delta z, that is z plus delta z to the power n minus z to the power n. Taking z as common, 1 plus delta z divided by z to the power n minus z to the power n. So, z to the power n to the top outside, inside that bracket term you have 1 plus delta z divided by z to the power n minus z to the power n. Overall we take z to the power n as common, you have 1 plus del z divided by z to the power n minus 1 is equal to z to the power n, evaluating the power of that particular term n as 1, we expand it binomially, 1 n delta z divided by z plus n minus 1 divided by 2 factorial del z divided by z square plus dot 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 up to del z divided by z to the power n minus 1. Minus 1. Here plus 1 minus 1 cancel out, taking delta z as common throughout the entire terms, delta z as common z to the power n term here we have the common term as Here we have to take common as z to the power n delta z divided by z. Taking as common, inside that a bracket term we have first n plus n minus 1 divided by 2 factorial del z by del z by del z by z up to the terms continue as del z by z to the power n minus 1, as we taken common as del z divided by n. Here we have z to the power n minus 1 delta z into n. All the terms, the power of del z by del as neglected. So we have z to the power n minus 1 del z into n. That is, here we take f z plus delta z minus f of z dividing the del z term to this side. So del z is equal to, that side we have n z to the power n minus 1. Now taking the limit on both sides, sorry, here the terms are existed, these terms are existed, but when we take the limit delta z tends to 0, altogether terms are 0 as delta z tends to 0. So we have that limiting value which is equal to f dash z is equal to n z to the power n minus 1, as we show that given function was f of z is equal to z to the power n, then f dash of z is equal to n z of n minus 1. Here del z is divided to that side, and taking the limit we have this value. So the terms are within there, plus n whole into n minus 1 divided by 2 factorial del z by z dot 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 del z by z to the power n minus 1. Now when that is divided to this side and taking the limit, so we have all together terms are cancelled out, only n term n exists. So the differentiation of that particular function is n z to the power n minus 1. So with the help of this video lecture we understand the functions of a complex variable, limit of complex variable, continuity of complex variable, differentiability of complex variables. So with this useful and informative notes, let me wind up this session. Thank you.